Air conditioning systems do not produce cold air. They operate by mechanically extracting thermal energy from an enclosed space. This extraction relies on a continuous refrigeration loop, driven by four distinct components: the compressor, the condenser, the expansion device, and the evaporator. Isolating the system to find where ambient heat is absorbed leaves us with the evaporator, the primary heat collection point in this loop. To understand how cooling actually works, we have to examine the precise thermodynamic mechanisms occurring inside this specific interface. We will look at how engineers manipulate fluid equations to design vastly different physical architectures, whether they are extracting heat from ambient air or industrial water. The design of the evaporator determines how much thermal energy a refrigerant can absorb without compromising the mechanical integrity of the system driving it. Looking at a 2D cross-section of a copper coil, heat absorption begins when high-pressure liquid refrigerant reaches a narrow expansion valve. As the fluid squeezes through the restriction, it experiences an abrupt pressure drop, simultaneously forcing the saturation temperature to plummet. This sudden drop ensures the fluid's saturation temperature sits significantly below the ambient temperature of the target environment. The resulting low-pressure, low-temperature refrigerant then enters the empty volume of the evaporator coil. Thermodynamics dictate that thermal energy always flows from high temperatures to low temperatures to reach equilibrium. Because the internal fluid is colder, warmer ambient air transfers its thermal energy directly through the copper wall. As this energy enters the liquid, it acts as latent heat, forcing the refrigerant to boil and vaporize. It is during this specific transition from a liquid to a gas that the fluid utilizes latent heat. This phase change is where the vast majority of heat absorption actually occurs. A simple fluctuation in temperature cannot absorb commercial-scale thermal energy. Forced phase change is the only mechanism powerful enough to achieve that. To calculate exactly how much heat a coil can absorb, engineers rely on this specific heat transfer equation: Q equals U times A times delta Tm. Q represents the total heat transfer. To increase capacity, engineers must maximize these variables. Looking specifically at A, the physical heat transfer area, a bare copper tube offers a severely limited surface. By adding dense rows of thin aluminum fins to the exterior, the effective contact area increases exponentially. But this creates a strict engineering trade-off. Spacing the fins too tightly together causes severe air pressure drops and creates traps for dust blockages. Because of this flow restriction, fin spacing is a calculated compromise based strictly on the specific application and the system's expected airflow. The final variable, delta T mean, is the mean temperature difference between the internal refrigerant and the external ambient fluid being cooled. On the internal refrigerant side, this cooling capacity can also be calculated by multiplying the fluid's mass flow rate by its enthalpy difference. Every physical evaporator design, regardless of shape or size, is simply a geometric strategy to maximize this mathematical equation without choking the system's flow. The requirement to optimize this equation results in drastically different physical architectures, depending on whether the system is cooling air or water. This diagram illustrates a DX coil, expanding refrigerant directly into tubes, making it highly responsive to rapid room temperature changes. By contrast, industrial water chillers utilize flooded shell and tube evaporators, submerging straight water tubes entirely in a large pool of boiling liquid refrigerant. Flooding the evaporator housing with liquid refrigerant offers exceptional heat transfer performance. However, these systems require complex oil return management logic to keep compressors properly lubricated. A third alternative is the plate heat exchanger, which uses alternating thin metal plates to achieve extremely compact, high-efficiency liquid cooling. Despite contrasting appearances, a massive industrial chiller and a residential window AC unit execute the exact same mathematical optimization of surface area and thermal dynamics. This optimization carries a specific mechanical hazard. Because liquids are incompressible, any refrigerant that fails to evaporate before reaching the compressor can cause the internal metal components to deform or fracture under pressure. Because compressors are designed to pump gas, not liquid, complete evaporation inside the coil is non-negotiable. To ensure this, engineers enforce a strict thermal safety margin called superheat. Superheat is the measurable difference between the actual vapor temperature leaving the coil and the underlying saturation temperature. If the boiling zone is 5 degrees and the vapor exit is 10 degrees, the system runs a safe 5 Kelvin superheat buffer. If the expansion valve overfeeds the coil, it results in low superheat. The boiling liquid line surges dangerously close to the exit of the tube, shrinking the dry vapor safety buffer and risking liquid floodback. Conversely, high superheat occurs when an underfeeding valve causes the liquid to boil off too early. This leaves a massive, inefficient expanse of dry vapor, wasting large amounts of the evaporator's engineered surface area. External factors immediately disrupt this delicate thermodynamic balance. A dirty air filter or low blower airflow lowers the overall heat transfer rate. This forces the evaporating temperature to drop below freezing, ultimately causing moisture in the air to freeze and form thick ice across the coil. Operating an evaporator is an eternal compromise. The system must push the coil to absorb maximum heat capacity while rigorously maintaining a strict thermal buffer to ensure the compressor's mechanical survival. When we pull back from the isolated view of the evaporator, these physical rules integrate directly into the full, continuous refrigeration loop. The cycle functions strictly as a mechanism for moving heat from one location to another, driven entirely by the aggressive manipulation of fluid pressure. Whether a technician is servicing a compact direct expansion coil in a residential unit, or an engineer is analyzing a massive flooded shell and tube heat exchanger, the underlying physics remain rigidly identical. Successful HVAC execution relies on flawlessly balancing the fluid mechanics of the refrigerant against absolute thermodynamic equations. System designers must continually maximize the surface area and heat transfer coefficient for optimal heat absorption, while strictly managing the refrigerant flow to maintain safe superheat levels. The evaporator is the component where the cycle meets its primary objective. It is the interface regulating the temperature of a physical space.